Imagine a world without smartphones, smart homes, or even digital watches. What powers these devices? The answer lies in a tiny marvel of engineering, the microcontroller. These minuscule computers, often smaller than a fingernail, play a crucial role in the modern digital age. They power our appliances, regulate our vehicles, and enable us to communicate with the world. Despite their diminutive size, their impact is monumental. Prepare to be amazed by the power and potential of these tiny computers. A microcontroller, often abbreviated as MCU, is essentially a miniature, self-contained computer system on a single chip. It's like a Swiss Army knife of electronics, packing all the essential components of a computer: a central processing unit, CPU, memory, and I/O peripherals like input-output registers and analog-to-digital converters, onto a single integrated circuit. The CPU, the brain of the microcontroller, fetches instructions from memory and executes them, controlling the operation of the device. The memory stores both the program instructions that dictate the microcontroller's actions and the data it processes. I/O peripherals act as the microcontroller's interface to the outside world, allowing it to communicate with sensors, actuators, and other devices. Think of a microcontroller as a conductor leading an orchestra. The CPU is the conductor, interpreting the musical score, program instructions, and directing the musicians, peripherals, to produce the desired music, device functionality. Each component plays a crucial role in the harmonious operation of the whole. Unlike general-purpose computers, microcontrollers are designed for specific control tasks within larger systems. They excel at real-time applications, where they must respond to events in the physical world with precise timing. This makes them ideal for controlling motors, reading sensors, and managing the flow of information in embedded systems. While the terms microcontroller and microprocessor are often used interchangeably, they refer to distinct entities in the world of electronics. Understanding their differences is crucial for grasping the unique role of microcontrollers in modern technology. A microprocessor, as its name suggests, is a processor on a chip. It forms the heart of a computer system, responsible for executing instructions and performing calculations. However, it lacks the integrated memory and I/O peripherals that characterize a microcontroller. A microcontroller, on the other hand, is a complete computer system on a chip. It integrates a microprocessor, memory, and I/O peripherals, allowing it to operate independently without the need for external components. This self-contained nature makes microcontrollers ideal for embedded applications, where space and cost constraints are paramount. Imagine a microprocessor as a skilled chef and a microcontroller as a fully equipped kitchen. The chef, microprocessor, possesses the culinary skills to prepare a meal, but requires a kitchen, external memory, and peripherals to work their magic. The microcontroller, like a kitchen, comes equipped with all the necessary tools and ingredients, memory and peripherals, allowing it to whip up a complete dish, device functionality, on its own. The world of microcontrollers is vast and varied, encompassing a wide range of devices tailored for specific applications. Microcontrollers are classified by their bit width, influencing processing power and capabilities. 8-bit microcontrollers are cost-effective and energy-efficient, ideal for toys and basic appliances. 16-bit microcontrollers balance power and cost, used in automotive and industrial applications. 32-bit microcontrollers handle complex tasks, found in smartphones and gaming consoles. To truly grasp how microcontrollers work, let's illuminate the concept with a simple example. Controlling an LED with a button. Imagine a circuit where a button acts as an input and an LED serves as an output, both connected to a microcontroller. When you press the button, it sends a signal to the microcontroller's input pin. The microcontroller, programmed to detect this signal, springs into action. It fetches the corresponding instructions from memory, which tell it to activate the output pin connected to the LED. This in turn causes the LED to light up. This seemingly simple operation encapsulates the essence of microcontroller functionality. It receives input from the environment, processes this information based on its programmed instructions, and generates an output that interacts with the physical world. The speed and precision with which it performs this cycle are what make microcontrollers such powerful tools for real-time control. The microcontroller acts as the brains of the operation, constantly monitoring the button's state and reacting accordingly. This continuous interaction between the microcontroller, the button, and the LED showcases the dynamic nature of embedded systems. The impact of microcontrollers on modern life is so pervasive that it's often overlooked. These tiny chips are the silent workhorses powering countless devices and systems we rely on daily, seamlessly blending into the fabric of our technology-driven world. Step into your kitchen, and you'll find microcontrollers diligently managing your appliances. They regulate the temperature of your oven, control the cycles of your washing machine, control the audio streaming to your wireless speakers, and even dispense the perfect amount of water for your coffee. These tasks, once performed manually, are now automated thanks to the tireless efforts of these embedded marvels. Even your mode of transportation is heavily reliant on microcontrollers. They govern the engine control unit of your car, ensuring optimal performance and fuel efficiency. They manage the anti-lock braking system, keeping you safe on slippery roads. They even provide the intelligence behind advanced driver assistance systems, paving the way for a future of autonomous vehicles. As technology advances at an unprecedented pace, the role of microcontrollers is only set to expand. They are at the forefront of emerging trends like the Internet of Things and artificial intelligence, poised to revolutionize the way we live, work, and interact with the world around us. The Internet of Things envisions a future where billions of devices are interconnected, seamlessly sharing data and coordinating actions to create a smarter and more efficient world. Microcontrollers, with their ability to connect to networks and process data, are essential for realizing this vision. They will act as the eyes and ears of the IoT, collecting data from sensors, controlling actuators, and enabling devices to communicate with each other. Artificial intelligence, with its ability to learn from data and make intelligent decisions, is poised to transform industries ranging from healthcare to manufacturing. Microcontrollers, with their increasing processing power and ability to run sophisticated algorithms, are becoming ideal platforms for deploying AI at the edge, closer to the source of data. This will enable real-time decision-making, reduce reliance on cloud computing, and unlock new possibilities in areas like predictive maintenance and personalized healthcare. As microcontrollers become increasingly integrated into our lives, it's crucial to consider the ethical implications of their proliferation. While they offer tremendous benefits, their potential for misuse cannot be ignored. We must tread carefully, ensuring that these powerful tools are used responsibly and ethically. One concern is privacy. As microcontrollers become smaller and more affordable, they find their way into more devices, many of which collect data about our daily lives. This data, if not properly secured and anonymized, can be used for surveillance, profiling, and other privacy-invasive practices. Another concern is autonomy. As microcontrollers become more powerful and capable of running AI algorithms, they are being entrusted with increasingly complex decision-making tasks. This raises questions about accountability and the potential for unintended consequences. If a microcontroller-powered system makes a mistake, who is responsible? Furthermore, the widespread adoption of microcontrollers in critical infrastructure, such as power grids and transportation systems, raises concerns about cybersecurity. A successful cyber attack on these systems could have devastating consequences. To mitigate these risks, it's essential to prioritize security and privacy in the design and deployment of microcontroller-based systems. We need robust regulations, industry standards, and ethical guidelines to ensure that these powerful technologies are used responsibly and for the benefit of humanity. Microcontrollers, despite their small size, have ushered in a technological revolution. These unassuming chips power the devices that make our lives easier, safer, and more connected. From the mundane to the extraordinary, microcontrollers are everywhere. Their versatility and affordability make them indispensable in many applications. As we embrace this tiny revolution, it's crucial to proceed with both enthusiasm and caution. We must harness microcontrollers for the betterment of society while being mindful of their potential risks. By prioritizing ethical considerations, we can ensure these tiny wonders drive progress for generations.